So good morning, everyone. Good morning. Can you guys hear me? So I think we are still 2 minutes away from the start time. Let me do the introductions quickly so we can focus on the content. My name is Vishwas Lele, and I work for a company called Applied Information Sciences in the Washington, D.C. area. I've been building Azure solutions, developing, architecting, designing Azure solutions for almost 10 years now. Got started when Azure came along. And my first introduction to Kubernetes was in 2015. I was watching, I was watching a hackathon back in 2015 summer, and one of the Microsoft employees, I forget his name, won that hackathon by building a visualizer for Kubernetes. And I had never heard of Kubernetes then. I downloaded that code and was playing with it, and that's how I got started. Never thought that that piece of visualizer or that technology would be so important today. So with this, I think I can indeed, we're still 30 seconds. The clock will start at 60-minute mark. So I have to fill this awkward pause with something else, maybe 30 seconds. And you probably saw me laughing is, I'm thankful to Microsoft for this is the first time they've done two things. One is they've allowed non-Microsoft speakers to speak at Build. So that doesn't mean you can leave now. You're logged into this session, right? I'm a non-Microsoft speaker. The other thing that they've done is that the first time they've allowed kids to come in, right? As an attendee, you're allowed to bring a kid. I hope many of you took advantage of that. I certainly did, and I was just calling my daughter and saying, for the next hour, please don't move, because as much as I love you, if you call me and say I'm stuck in the elevator, I would have to say, please stay there for 60 minutes, and I'll come get you right after my session ends. So please stay wherever you are. Don't move, don't do anything. With that, let's get started. Okay, so you've seen this slide for 10 minutes now, and let's just move into, before I show you the agenda, let me just show you this slide, which is sort of the mental picture of what we are trying to accomplish in this session. So this is sort of the tagline for the entire session. The goal behind this session is combining the power of a cloud-native service like AKS and combined it with a managed database service like Cosmos DB. That's sort of the tagline. And then we will go through the entire session and try to keep coming back to this tagline of ours, if you will. So here is the agenda. I'll start out with the definition of a cloud-native application. And given the time that I have, I'm going to assume a working knowledge of AKS and Cosmos DB. And some of you probably have a working knowledge, and some of you are looking at this for the first time. That's OK. If you're new to this, I'm going to give you enough glimpse to understand AKS and Cosmos through this session, even if you're new. But then you can go back and look at some incredible resources, helpful resources to go back and shore up your understanding, and then come back and watch a video of this session so you'll get value from that. So define cloud-native apps, define stateful cloud app considerations. Then we'll talk about cloud-native tooling. We'll talk about service broker. We'll talk about site reliability engineering. And these are all sort of connected themes, because as you start talking about stateful applications and you start talking about external applications, then you have to think about, how am I going to do site reliability engineering? Now I have an external moving part. How do I deal with that? And then some discussion on portability, multi-cloud, and things like that. So what is a cloud-native application? And this term is being used so much these days that it has become a broad term. So it makes sense to just have a quick definition of that term here, and I'm going to use the CNCF definition. And CNCF, of course, is the Cloud Native Computing Foundation. It's a sub-foundation of Linux Foundation, manages Kubernetes, and manages many other projects. So the key tenets of the Cloud Native application are, and I have a link at the bottom of this slide. I sort of parse that page and put it into some 4 bullets. First and foremost, scalable distributed applications that can run across public cloud, hybrid cloud, and private cloud. Why this is important? Because you're running in a decoupled state. You're not directly dealing with the hardware layer. You are decoupled, and by virtue of that, you're able to run that application across multiple providers. Okay? Systems are typically loosely coupled, which means your application is broken up into small parts. Each part has a well-defined interface as an API, and because you have these small parts, it is more resilient. One failure in one part cannot impact the whole application. And because you have a well-defined interface, they're more observable, they're more manageable, and things like that. And then you have a whole notion of concepts like containers, which everybody knows is a packaging format and a deployment format. And then you have things like microservices. Of course, we don't have time to talk about microservices as much here, but think of microservices as small units of code. Think of single responsibility principle hosted inside a container. And the other interesting aspect of a cloud-native application is that it is based on an immutable infrastructure that is typically deployed using a well-defined API or a desired state configuration. I'll talk about that, what that means in a moment. Cloud-native applications are based on an ecosystem that is fostered by CNCF. Kubernetes itself is a project managed by CNCF, and then there are a whole host of other projects, of course, that are open source, vendor neutral, etc. Last but not the least is robust automation. If you've been working in the cloud, you know the key to success in cloud is automation. That automation becomes even more important in a cloud-native sense because you have multiple parts, multiple moving parts, every part exposing an API, a version associated with each API. So the system is highly dynamic. You're scheduling these microservices pods. Maybe you're doing blue-green deployment. You are doing traffic routing. You are making these high-impact changes to your application, and the only way you can make high-impact changes to your application is by having robust automation. So those are the key bullets, and they come from the charter of CNCF itself. Okay, now that we have an understanding of a cloud-native application, let's shift gears quickly and talk about AKS. So what is AKS? AKS is a way for you to get Kubernetes inside Azure, as simple as that. But it is not just about getting Kubernetes in Azure. It is also about thinking of all the things that are listed on the left-hand side of the screen. So Kubernetes gets deployed on a bunch of machines. How are those machines going to get patched? I don't want to patch those machines. How about high availability? I was here for KubeCon a few months back, and it was amazing to see the number of people attending. And I went to many sessions where we were talking about production lessons and things like high availability. How am I going to take my etcd database, which is the config database behind Kubernetes, and making it production ready? All of those kinds of things are important considerations. Self-healing, monitoring. So if you look at the right-hand side of the diagram here, as a user, you come in and you say you want to deploy an application, you go to a Kubernetes endpoint, and then you go to the master node or the control plane and say, hey, create these applications for me. And the master node has all the things that I talked about, etcd database, which has to be highly available, has to have a scheduler, reconciliation loop, cloud controller, and so on and so forth. This would be quite hard to manage by ourselves, and fortunately, Azure does these things for us automatically. So this part is completely managed by Azure, and that's sort of the key point. What is AKS? AKS Kubernetes combined with enterprise capabilities like you want to combine the identity plane with maybe Azure AD or ADFS. Maybe you want to have log analytics integrated with Kubernetes. So it's the combination of the two together. And of course, at the bottom of the screen, this is where your applications reside. Okay? So that's what a quick example of what Kubernetes is. What I'm going to do is shift quickly to a demo here. And let me go to screen 6. Tell me you can see it. So what I've done is, because I've only 60 minutes, I've tried to pre-provision some steps to save us some time. So here is this application. In fact, before I go to the demo, it will help for a second, apologize, to see the slide first. It would make sense here. So let's see the slide first. Okay, so this is that application. This application was originally developed by a colleague of mine, Gautam Shah, who works with me, and we took that application and extended it for the purposes of this talk. Let's walk through this diagram. It looks busy, but let's just walk through this quickly. It's a very simple application, but at the same time has just enough complexity to bring out the concepts. So I have a microservices-based application called Book Review. It has a bunch of microservices, and they follow principles of bounded context and things like that. They have persistent store associated with them, so there are a bunch of services there. As you move to the right of that, all of these microservices are written in ASP.NET Core. They are based on The persistent store is either SQL Server running in a container or a Mongo DB container. So those two persistent stores. Moving right, you have the source code structure. And then once you have the source code structure, you typically have a Docker file associated with that. You go through the Azure pipeline, and you will end up with a container image, all right? And then what you do is you take those container images, and you push them to some sort of a registry. In this case, I'm pushing it to the Azure Container Registry. So everybody with me so far? So application, this is, of course, the build and deployment view of things. To the far right of this diagram are a bunch of Kubernetes specifications. And I strongly feel that this is one reason why Kubernetes is so popular these days is up until now, if you look at that orange box, I've defined my containers, my usual Azure pipeline, but then how do I translate that into a running application? And that's where the Kubernetes specifications come in. We'll see that in a second. So let's just go to my machine here. And I'm going to go into Visual Studio Code. This is the entire application right here. In fact, if you go here, these are all of the microservices. And nothing very earth-shattering about it. This is just standard ASP.NET Core, controllers, and things like that. So okay, we won't spend too much time on that part itself. What we will spend time on is, let's just go into so I'm going to come out of this here, and I'm going to go into the Kubernetes specification, and let's just bring up this deployment file here, okay? And I know for those of you who have not looked at the YAML deployment file, it might be intimidating, but think of this way. So I've taken my code, I have them in containers, and here is my, if I go to the Azure portal here very quickly, let's just bring up the container registry here, and if I go further down, I'm going to the repositories here. These are all my Docker images inside my Azure Container Registry. Okay, so just think with me for a mind. You've run the Azure pipeline, taken the source code, stored everything in a Docker registry here. Okay, going back to Visual Studio here. So deployment is a first-class notion in Kubernetes. So here I'm saying, hey, create me a deployment, and oh, by the way, create me 2 versions of these microservices or 2 replicas of this microservice. And oh, by the way, this microservice is powered by this container, and you can go find this container image from this location. As simple as that, okay? So let's do this. Let's just change the replica count to 3 and save it. And let's just try to, let me go to my other PowerShell window, and let's just apply this change, okay? So you have to see at the bottom of the screen, hopefully I can just bring it up right here. You can see all I'm doing is kubectl apply. Anybody watch Scott Hanselman's blog post or many years back about how many keystrokes do we have before we die? Have you seen that? So I didn't want to type kubectl all day long, so I just have kubectl converted into aliased into k. So k apply this, and now let's run this here. And by virtue of running this Kubernetes specification, a bunch of things are happening for us automatically. It is going to go find these pods, deploy my container images there, and not only that, let's look at another file here for a moment. Let's look at the service file. So containers are ephemeral, they come and go, so you need some sort of a load balancer in front of them. I can just run a file like the service YAML file, and the real beauty of this is that I am not directly connected to the underlying Azure IaaS, right? In this case, I'm asking for a load balancer, but I'm getting a load balancer by virtue of deploying a service of type load balancer and annotating it with an Azure load balancer attribute. And this is all I need to get myself a load balancer in Azure, and I don't have to worry about that. So the reason I'm sort of explaining this again is it goes back to my notion of a cloud-native application being decoupled from the underlying infrastructure. Okay, so let's see if that worked. Let's just go back to our cluster here and see if we did indeed get, so looks like, so there you go. No, looks like every time I have to show the Kubernetes portal, I need to open a tunnel, and if there is no activity on that tunnel, that gets timed out. So it looks like it did get timed out. That's no problem. Let's just go back and start this again. I'm going to clear this mess a little bit up here, and let's just start the Kubernetes portal again. So keep in mind, the Kubernetes portal is all inside my virtual network, right? It is not visible to the outside world. That's why I have to establish a tunnel. And now find the right namespace. And if I did things correctly, we should see a third pod. And we do indeed see the third pod right here, okay? So we see 3 replicas of our service running. So that's an important concept to note here. And what is also interesting is, since I specified, and this started a minute back, since I specified that I needed 3 replicas running all the time, if I go in and delete this, you will see that it will start a new pod again automatically. So the system is not only decoupled, it is also self-healing and providing that health checking and things like that. All right, let's just go back to the slides for a moment. So you were looking at this slide, you were looking at the far right of this diagram where we were taking our binaries and container images and then deploying it to the cluster. Let me quickly show you the runtime view of that. So here is the runtime view. All of those deployment files that I ran in the previous demo are shown up here. So in this case, the Kubernetes cluster got deployed to my virtual network. So the outside box is the Azure subscription, as you would imagine. Inside box is the virtual network. Inside the virtual network, I have the load balancer, and I showed you that load balancer got deployed. The various microservices got deployed, and then Mongo DB was also deployed, not part as the last step, but I'd already deployed it ahead of time. So this is sort of the runtime view of things. I'm going to drill into the Mongo DB box in a second, but otherwise, this is sort of the physical or the runtime view of the cluster as we see it. All right, so let's just keep going here. I'm going to show this to you in a second. So up until now, we were talking about a cloud-native application that was essentially stateless. I did mention that it is running SQL Server and MongoDB, but I really didn't get into how the state is stored. So let's take a look at that in a moment here. So in order to talk about the state, it is important to understand some key concepts, and then we will go back and look at how MongoDB has been set up. So first and foremost, people have been running stateful application in Kubernetes for a long time. In addition, there have been a number of improvements in Kubernetes, and I've called some of those out. First is stateful set, I believe came around in Kubernetes 1.6. So I showed you pods being deleted and being recreated quickly. They had no stickiness, they had no unique identifier associated with them. Stateful set is designed for a workload where it is important for you to create the pods in a certain order and delete them in a certain order. So that's stateful set. Then there is notion of container storage interface. In early days of Kubernetes, if you wanted to talk to a storage, the plugin was included in Kubernetes itself. But now that code has been moved out and there is a standard interface, and everybody, whether you're a NetApp or something, you have to implement that interface. The second line that I want to talk about quickly is the persistent volumes and persistent volume claims and things like that. So what are these? So how do you persist state inside a pod? Because pods are coming and going all the time. How are you persisting them? Well, it turns out as an administrator of Kubernetes cluster, you can set up a persistent volume. And if you are in Azure, you would typically set up a persistent volume using something like an Azure disk or an Azure file. So as an administrator, you set up a volume. And then as an application developer, when your pod is coming up, you make a claim for that volume. And remember, I said this whole system is highly dynamic. So when a claim is made, it will go find me a volume and mount it and attach it to my pod. And when my pod goes away, my state is persisted. And then next time I come back up again, Kubernetes is giving me that same volume. That's how my state is persisted. So these are all things that have been made available in the last couple of years. So persistent story is getting better. I also want to quickly talk about operators, which is all rage these days in Kubernetes. So the concept of operators, it is about taking the operational knowledge associated with something like you want to run MongoDB inside Kubernetes. You need to understand operationally some best practices of how to do that. Rather than having you write a script to do that, you can get an operator registered in your cluster, and that operator will do those kinds of things for you. So as you can see, there are a number of concepts that can help you with persistent store. Let me now with an understanding of these concepts, let's go back and see how MongoDB was set up in my existing application. So I'm going to go back to my machine, and I'm going to bring up how MongoDB was set up. So the first and foremost, remember I explained to you the stateful set? I create a stateful set where my Mongo nodes are going to be running. So that's the first part. And then I also define a service like I defined the last time. And then I have a config map here. What is interesting is in this config map, I pass in a script here. And we won't go through this whole script by any means, but I just wanted to show you that I had to do a bunch of things to make it a highly available MongoDB instance. I had to have the script run every time the pod starts, make sure it is the right instance, make sure the replication set is ready, and my node is coming up. So there are a few things that you have to do for this MongoDB instance to work. And as you can see from my comment, sometimes there is a timing issue, and I'll have to restart my MongoDB instance and things like that. So yes, my stateful application is running inside the Kubernetes cluster as part of MongoDB, but I had to write all of this code to get that running inside my cluster. Okay, let's go back to the slide. So we have seen some challenges of how state can be managed. Turns out that, and you can't have a Kubernetes presentation without a Kelsey tweet. And I didn't get any laughs because that's an inside joke. It's not my joke. If you were at KubeCon last year or seen some videos, that's a joke that Kelsey was tweeting, and you have to have a tweet from him in your slide deck. So anyways, what the tweet is suggesting is there have been a number of improvements of how you can run stateful applications in Kubernetes, but there are some scenarios where you may need to go to an external service. And let's take a look at some of those scenarios. One of them is, what if we wanted to do a geo distribution, right? What about, I showed you in the previous slide that you had to set up this cluster, you had to run the script to make sure that your MongoDB cluster is highly available. What about elastically scaling out? I can create more MongoDB nodes, no problem. I can run a kubectl commands and say, give me more MongoDB nodes. But what if I wanted to go from an Azure disk to some higher performing disk subsystem in Azure? I would have to write some automation to do that. I just can't elastically scale up and down. And then what if I wanted some performance guarantees on read and write and things like that? So the point I'm making in this slide right here is that even though there have been a number of improvements in terms of state management in Kubernetes, there are some scenarios here where you may want to go to an external service that gives you these kinds of capabilities. Okay. So let's keep going and talk about Cosmos DB here very quickly. So Cosmos DB is a globally distributed database service. And as someone who has spent maybe 3 or 4 years trying to make applications resilient, many of our customers run mission critical applications on Azure. And an important part of that is looking at that application and making sure that those applications can survive an outage. So you typically end up doing a lot of work where you have an instance of the application running in one region, you have another instance of the application running in another region, then you have to have the right monitoring in place and make sure your application can fail over to the second region, right? So there's a lot of work that you have to do to make your application resilient to a failure situation. What I love about Cosmos DB is that it is designed as a cloud-first service, which means that kind of resilience, the geo distribution is baked in to that. So you can see at the bottom layer of this ring, it has turnkey global distribution. So all you need to do is come in and say, add another region. It gives me an elastic scale out. So in the case of MongoDB example that I mentioned, I can add more pods, but I would have to change the disk subsystem in order to get a better throughput. In this case, I can just simply change scale dynamically and elastically what my throughput is. Okay? I can get an availability guarantee, and not just availability guarantees, I can get a guarantee on read and write. So you can see a bunch of advantages that I have. It is a NoSQL service, so it supports key value, column family, document, etc. But what is also very interesting is that MongoDB supports at a protocol level things like Mongo, Cassandra, Gremlin, etc. So you are able to take your existing Mongo database and move it to Cosmos and then use your existing Mongo clients to talk to the Cosmos database. Everybody with me so far? So we are trying to, you can see where I'm headed, right? We talked about a cluster which is running Mongo locally. We talked about Cosmos, and then we'll talk about how we can take that application over there. So quickly talk about two other interesting aspects of Cosmos DB, and then we'll move along. As I said earlier, it has protocol level access for things like MongoDB, which we'll be using. This is brand new. You may or may not have seen this. This was announced about 3 months back, where it also supports the etcd API. And I think this is huge because now you can use Cosmos DB as the backend store for your Kubernetes clusters. So because they have a multi-model database, it is easy for them to add new models. And one of the models that they added was the etcd or the Cosmos etcd API. Okay, and this diagram just says it, that I'm just using the MongoDB wire protocol. And moving on, so what about cloud native tooling? So I'm going to shift gears, and I'm going to ask myself this question that, okay, you've made a case that state inside the pods was not as easy, and you made a case that I should go to a managed service, which is a geo-distribution enabled. But let me ask myself this question that if I do that, am I not moving outside my cloud native tooling? Okay. What do I mean by that? So if I'm within my Kubernetes cluster, I'm typically using my kubectl commands, my YAML files to deploy everything. Okay. As soon as I introduce an external entity, in this case a Cosmos DB, then I have to go outside the context of my cloud native tooling, run a PowerShell script perhaps, go get myself a Cosmos DB database, get a connection string, pass it into a manifest as part of my Kubernetes cluster. So some people I talk to, or some customers I talk to, are concerned that, hey, am I not going outside my cloud native tooling? That's a good question to ask yourself, and this is what we're going to talk about next. And before I bring up the next slide here, I just wanted to show you what it would look like if you had to do this manually yourself. So let's go back to my machine here. And I wanted to show you, let's just go to this right here. And these are all my snippets. I didn't want you to see me typing this, but I just keep. So right here, I would have to first create a Cosmos DB database. I would have to specify the IP range filter. I would have to specify the consistency levels. I would have to define the locations, and so on and so forth. I would have to do all of these things in order to get myself a Cosmos DB database. And then I would have to get the connection string. I would have to then pass it inside Kubernetes. I would have to write this as part of my PowerShell script. Okay? With that in mind, let's just go back to the slide and see how we can solve that problem using a notion of open service broker. Okay? So there's a new specification. This specification really is about the ability to integrate your cluster with an external service. So it's called the open service broker. And the idea behind is really simple. In fact, this diagram will help you. So the idea behind this is very simple. You essentially install the open service broker as part of your Kubernetes cluster. And once you've installed this broker, you can go to this broker and say, give me a Cosmos DB connection. And you will be given a Cosmos DB connection at this point. All the connection details would then be stored as part of a Kubernetes secret, which is a first-class object in Kubernetes. So let me actually show you this diagram. This will make more sense here. So I'm abstracted from the underlying details of how to set up Cosmos DB and run PowerShell script and things like that. All I did was I installed the broker. And then once I installed the broker, I was able to say, hey, show me all the services that this broker can give me. And once you have all the services, show me the plans. So each service may have multiple plans. What do I mean by the plans? I could have a free plan, I could have a standard plan, I could have an advanced plan, something that has been simplified from a Kubernetes perspective. So give me the plans, and now I want to go create an instance of that. I know which plan I want, go create me an instance, and the final thing I need to do here is I need to go bind it to that instance. And what binding essentially means is, in this case for my demo means is, give me the connection string. I will take that connection string and then store it as a secret inside my kubectl object. So everybody with me so far? Let's just go do a quick demo of this. So you can see my screen here. And let me just clean this up. So I'm just going to run these commands, and I'll explain them as I run them. So the first thing I'm going to do is I'm going to get what cluster service broker have I installed. And let's run this. Okay. And let's open the output. It's just easier to look at it here. So in this case, the only cluster broker that has been installed is the Azure broker right here. So I've installed the, right here you can see, it is the open service broker for Azure. So that's the broker that I've installed. I didn't want to install it as part of the demo because it takes 2 or 3 minutes. So I went ahead and installed it. So this is the broker that is installed. Let's look at all of the classes that this broker offers. So let's run this command. And let's look at the output here. Right here. So you can see here that this broker supports a number of classes. And in this case, we are, of course, interested in the Azure Cosmos DB instance here. It's further down here. So these are all the classes it supports. The next thing I want to do is, hey, show me all the plans. Let's run this also. And these are all the plans that are available. Okay? So I have a premium plan, basic plan, and things like that. And the last thing I'm going to do is create an instance. And once again, creating an instance can take a couple of minutes because, as you can imagine, it is going to go to Cosmos DB, create an instance. So I already created it. All I'm going to do is show me the instances that I've created. Let's run this here as well. And you will see that I have one Mongo DB instance that I've created. So everybody clear on this? We got the services, we got the plan, we created an instance, and the next thing we are going to do is retrieve the binding, if you will, here. Let's just go get the binding. And you can see the binding right here. And in fact, the better way to look at the binding is actually using kubectl. So let's just do a kubectl command and get the secret. Remember, once the binding is complete, that binding information is stored as a kubectl secret. Let's just dump that out. And did I run this yet? It was stored in output YAML. So right here is our binding. And you can see here that I got a connection string, which was the Mongo DB URI connection string, and I got this binding from there as well. Okay? So this is the notion of the service broker. One thing we have not done yet is looked at the application. So let me do one other thing. So how do we, our application right now, the way it is deployed in our cluster is, I have a bunch of pods that are running all these microservices, and then these pods are using the Mongo DB pod as the persistent store. That's how things are right now. On the side, what we did was we went ahead and installed Service Broker and got ourselves a connection to Cosmos DB. Okay. So how can I go in and switch my microservices to now start reading from Cosmos DB instead? Okay. So that's what I'm going to do next here. And for that, while I'm doing this here, let me also run the portal one more time here. Let's get the dashboard one again time, and then let's just go back here. And what I'm going to do here, and yeah, that's where the portal is coming up. Good. I'm going to run this command here. This time I'm going to apply a slightly different file. You can see I'm applying a deployment file which has Service Broker enabled, and I'll show this to you in a second here. So that file should be right here, and all I'm doing in this file, everything else remains the same. I'm telling my microservice that OSBA is enabled. That's all I'm doing, okay? So let's just run this deployment command here. This will cause all our services to get restarted, because now I'm telling them, hey, you need to go to a different database essentially. So if I go back to the portal here, and if I go back to the pods, I need to change the namespace to book review, sorry. And you will see here that I have these pods running, and this started 27 seconds ago. If I go look at this here, I should see that OSBA is turned. So OSBA has been set to yes. Okay. So this pod got deployed already. Okay. So I've not shown you the application just yet. So let's just go find the ingress controller, and let's bring up our application. And here's a very simple application. Let's just submit a comment. Rating is 1, whatever, and submit. So I've submitted a comment through this microservice, and looks like our comment got submitted. If I go to Visual Studio Code here, and if I go into Cosmos DB, and if I refresh this, you will see this comment here already. So I was able to switch it. So the thing to take away from this last demonstration is that we were able to get the benefit of a managed service like Cosmos DB without leaving our cloud native tooling, because the Service Broker did all the work for us essentially. Okay? Let's just go back to the slides. So the next question that we need to ask ourselves is, what about site reliability engineering? Because yes, that you found a way to do cloud native tooling, that's great, but you've now added more work for me, essentially, because now I have to not only monitor my cluster, and I have all kinds of operators running in my cluster which tell me if something goes wrong. You have now introduced another moving part in my application, and my site reliability engineering is a bit more complicated now. So how do I deal with that situation? So in order to answer that question, I wanted to go back to the portal here for a second. Let's just look at the quickly, go back to the Azure portal. And let's just go to a dashboard and go to Cosmos DB. This is the instance that my microservice is connected to. And I want to point out a couple of things here. So what does it entail when I talk about site reliability engineering? What do I mean by that? So one of the things that I talked about earlier is I should be able to replicate my data to another region. So if there's some sort of an outage, my data is still available. Furthermore, my connection strings should be smart enough to detect that there is a failure in one region and automatically redirect me to the other region. That's one important aspect of site reliability engineering. The other aspect is I get a sudden burst of load. How can I scale up to meet that load and then scale back down because it is expensive to operate at that level? These are some of the considerations that you have when you're writing a highly reliable application. And in case of Cosmos DB, if I come in here and go into, so we brought up the Cosmos DB explode here. I can simply come in here, and right now my application is deployed to one region, and that region happens to be US East right here. I can simply come in and select more regions, and just by virtue of selecting those regions, that data will get automatically start replicating across these regions. So, and right now as things stand, one of the region is writable, all the other regions are read-only, but that can automatically change if something were to go down. Not only can I set geo-replication, I can also set up consistency levels. So I can say that these two regions have a defined consistency level. How well in sync do I want these copies to be? I have an ability to control that as well. So that's one. The other thing I want to talk about is scaling. So once again here, I'm operating here with a certain number of request units. I can, using an API, I can just scale these request units up without having to do anything. With MongoDB instance, I showed you, I would have to write a script to add more pods. I would have to change the disk subsystem to a higher performing disk subsystem. I don't have to do any of these things. And the interesting part is that you can scale storage and throughput separately, and that's an important consideration there as well. So let's go back to the slides here for a moment. So we talked about improving, in fact. So even with an external service, we have sort of countered our question, which is, I now have to deal with multiple moving parts. I would submit to you that because this service is geo-distributed, I don't have to do the site reliability engineering here. In fact, let me show you one other capability called the MultiMaster capability. MongoDB does not even have a notion of a MultiMaster support. What do I mean by that? You can now write to multiple regions simultaneously. And since you're able to write to multiple regions, you really don't have to think about failovers, essentially. You are writing to both scenarios or both regions. And since you're writing to both regions, there is a possibility that a conflict might happen, right? And there is a conflict management that is built in here. And that's what I talk about here, that the last write wins conflict management is enabled. So you're going beyond sort of the core capabilities of MongoDB and enabling a multi-write capability as well. So how do you enable multi-write? You can see at the bottom of the screen, you can enable or disable MultiMaster support at the bottom here. So you can do that. And at this point, you can see on the right-hand side of the screen, maybe hard to see, that two of my regions are writable. That's only possible when I've set up the MultiMaster support. So two of my regions are writable at this point, and I can. So the code, I'll run a quick demo of this for you in a moment here, but at a high level, this is what the code looks like. I set up a connection policy. I say that I'm going to be using multiple write locations. I add my preferred regions at the bottom. And that's how I create essentially my application here. So let me just go ahead and run this application. So I have Visual Studio with an application. So I took that MongoDB collection that we were looking at. So remember, I submitted a comment. That was a MongoDB collection. I took that collection and created another Cosmos DB database, which has a multi-master write capability. And what I'm going to do essentially in this program, this is a multi-threaded program, and I'm going to write to two regions at the same time. And this is quite interesting. Even though I'm writing to two regions at the same time, you would think that there would be a conflict that would come up, right? That is expected. What is interesting about this demo is, as soon as I write to the one region, Cosmos DB quickly replicates that record to the second region. So you will find that in some cases, even before I go and do a write to the second region, that record has been replicated to the second region, and I get an exception saying this ID already exists. Make sense to everybody? So this is one of those programs where if things go right, there's an exception. Okay, because I'm hyper focused on showing you conflict, and Cosmos DB is working too hard and actually replicating my record to the other region faster than I can through my multi-threaded program. In case my record is not replicated to the second region, my writes on both regions will succeed, and at this point what will happen is, this is the last writer wins conflict resolution, and this conflict resolution is limited to MongoDB. If you were using something like a docDB interface, you could do more things with it. You could write a stored procedure which they will call, and you can do the conflict resolution yourself, or you could write some custom code to do conflict resolution. Since this is MongoDB and they have to be true to the MongoDB protocol, they can't add any things on top of that. So the only available conflict resolution mechanism is the last writer wins. So there's a server-side timestamp for every row that gets written or every document that gets written, and they compare the server-side timestamp across two regions, and the last timestamp wins. So let's go ahead and take a look at this program right here. Let's run. So I'm going to connect to Cosmos DB first here, and I'm going to detect how many regions do I have, and this is the most interesting part of the program. You guys should have told me to switch. So let me run this program again. So essentially a console program copied that collection over to another database, enabled MultiMaster write, and now let's run this program. First thing we are going to do is establish a connection to the two instances. And this is, so let's just go ahead and run this. And we are connecting to the US East and US West regions. And as you can see here, let's go up here. So in this case, I was able to generate a conflict right here, as you can see. This is the part I'm talking about. And so this was the ID that I wrote from the US East. This was the ID that I wrote from US West, and conflict was able to be generated because Cosmos DB did not have enough time to replicate the record over. Both writes succeeded, which means I did not get my exception. And Cosmos DB then went in and looked at the timestamp. Whichever server's timestamp was higher, it declared that record as the winner, and you can see that right here. Okay. Make sense to everybody? So what did we accomplish as part of this demo? If you sort of take a step back and think about it, we have now been able to deploy our application, even though it is an external service, we have been able to deploy it using CloudNative tooling. And we have been able to, in fact, enhance our resilience of our application because we have the ability to scale up and down using an API. We have the ability to geo-distribute it, and then we also have the ability to do things like MultiMaster. And not all applications, of course, can take advantage of MultiMaster, but the applications that can indeed take advantage of MultiMaster, this is the way to go, because we are spending far too much time trying to put all the monitoring machinery in place and figure out that my application is down and then failing it over to the other region. If you have both the regions active and you have some sort of a reconciliation mechanism, that's the way to operate in the cloud and avoid the 2 a.m. calls that happen when one region is down, are you failing over, and things like that. So that's an important part. Let's just go back to the slides here. I should be able to leave about 5-7 minutes for questions. Just hold your question just for 2 more minutes, sir, and we will get to that here. So the last thing I want to talk about is portability. So you have now moved me outside a cloud native context. I just don't have a kubectl and a YAML file which will deploy my cluster. How does it impact my portability? So hopefully you followed along. The theme of my talk is ask some questions of myself and try to answer these. And sort of this is the third in the series of questions. So first was cloud native tooling, site reliability engineering, and this one is portability. Have I not created a problem for myself? Have I not now tied myself to a certain provider where my application is running? What if I took this application and tried to move it to another cloud provider perhaps? So assuming that you want to move your application to another cloud provider that also has a service broker installed, your calls to that service broker will result in the calls to the cloud provider offered broker. So you went to Google Cloud, for example, they have a hosted broker. Now, I have to caution you that this is not as seamless as it sounds, because you might be able to get a Mongo DB instance in Google Cloud or some other cloud, but the binding information may be slightly different. So in this case, I was expecting the binding information to be a certain state, and I was able to just roll with that from my local Mongo DB to Cosmos DB. I could handle that, but if I took this application to the Google Cloud and they returned me a binding information that is slightly different, then I would have to make some changes. The way people are dealing with that is you essentially create a Helm package, and we have not talked about Helm, but think of Helm as a package manager for Kubernetes. And what people are doing is, inside the Helm package, you can deal with differences in the cloud. So absolutely, people are taking applications like the one I showed you, moving it to another cloud provider, and dealing with the differences that may be between the clouds using something like Helm. There may be other ways of achieving that as well. The notion of the service broker is actually quite simple. There are only 3 API calls to implement, and you can pretty much do anything you want. So you saw in the keynote yesterday, they talked about in AKS being available inside Azure Stack. So how would an application like this work if I move this to an Azure Stack? Well, you would be able to write a broker if you wanted to, if you just wanted to test it with something locally there. So think of portability from the context of what brokers are available and how can you deal with differences, if any, between them. So that brings us to the close of this talk. I want to bring back the tagline, if you will, for a moment, and that'll leave us about 8-9 minutes for questions still. I want to bring up the tagline and sort of bring it all together for you guys. So we saw that Kubernetes allows you, or AKS allows you to build cloud native applications by decoupling from the underlying infrastructure. We looked at the YAML files. We didn't have to make load balancer calls ourselves. So it's a very powerful way of building your microservices-based applications. And there's a number of tooling options that are growing rapidly every day. You want to take advantage of that. But how do you want to deal with state? And most of you will agree that we are all building stateful applications. How do you deal with the state? Take a look at what Kubernetes is offering, stateful set, persisted volume claims, persisted volumes, look at that. But then look at how you can combine it with an external service, which can offer you far more capabilities, like the geo-distribution we talked about. And then how can you incorporate those services in a manner that still keeps your application deployment portable? So that's essentially the focus of the talk. And I have a few minutes for questions. I urge you to go to the mic so that your questions can be recorded. And if you don't want to work, I will repeat your question, but looks like you are.
So my question was, with the multi-region right, we know what happened to the winner. What happened to the loser, and how did the application know that it lost in that conflict resolution? How did you handle that? How would the application handle that?
So the question is, you showed me how the conflict resolution happened. You showed me the winner, and essentially I showed you the winner by querying the database and seeing which record won. But in this case, Cosmos DB has a change log capability as an API available to you, which gives you a full audit trail of events that have transpired behind the scenes. And you could read off of that change log and figure out what happened and do something custom with that.
So in real time, the application, so you're a user, you're on a front-end application, and it loses all kinds of updated records.
Yeah.
That end user is a real person sitting around, could get an error message. How does I have to know?
So you would have to make that API call and figure out how this happened, that there's a conflict that happened, and then deal with it in that manner. I can, if you stop by, I can actually show you the code that's doing that, and then we can take it there. Any other questions? Okay, if there are no further questions, I'd be available outside the room for a few more minutes. You've been a great audience. I thank you for that.